0.6 matrix operations. The first thing we're looking at is that you can simplify matrices using the given operation. So we're going to first look at the basics of addition and subtraction and scalar multiplication. Those are the easy ones. So when we say given operations. And then the last one we're going to look at is multiplying matrices. That one's a little bit more challenging, but not bad once you figure out what the operations are that you're supposed to do to get the numbers. All right, so a matrix is an array of numbers in rows and columns. An array of numbers, and it doesn't have to be numbers, or I should say elements, but I put numbers, in rows and columns. An element is a number or variable in a matrix. A number or variable in a matrix. So, and we've already worked, since we've done 6.1 already, we've already worked with matrices, with augmented matrices, to write equations or put them in each row. But right now we're just looking at what are the definitions of a matrix. Now, these are also called A subscript RC. So you'll see A with a subscript number, and that number is actually two numbers. The first digit in that number is the row position. So it's where it's located, which row it's located in. And C is the column position. The dimensions of a matrix are R by C. They're always written as R by C, number of rows, by number of columns. What's a column? Is it horizontal or vertical? Vertical. Columns are vertical, rows are horizontal. So when I look at the first example, it says use this matrix, matrix A, with elements 4, 9, negative 18, negative 2, 11, and 3 to answer the following. State the dimensions of matrix A. Well, it's row by column. How many rows are there? 2. And there's 3 columns. So it's a 2 by 3 matrix. Letter B says find the value of A subscript 1, 3, not A sub 13, but A subscript 1, 3. That means I need to go to row 1, column 3. Row 1, column 3, the element is negative 18. Find the value of A sub 2, 1, not A sub 21, but the element located at A sub 2, 1, which means row 2, column 1. Row 2, column 1 is negative 2. Try this for matrix B. Try the problems underneath matrix B. So the correct answers for D, E, and F are 3 by 3, 18, and 34. Next, we're going to talk about adding and subtracting matrices. We're going to make a note in the margin over here. Just like when we're subtracting polynomials, I don't want you to treat it as subtraction. I want you to change the sign, just like we would on every term in the expression, in the equation, and then combine like terms. We're going to change the sign to subtract. We're going to change the sign on every element in the matrix and then add. For some reason, very few people, I've had the exception of maybe 1 or 2 people per year, even that's rare, who can actually treat everything as subtraction and get every single problem right, every single element, every single equation when they do that. And the rest of us, myself included, make an error somewhere in there. It might just be 1, but it'll mess up your entire answer. So for precision, we want to make sure that we change the sign on every element and then treat it as an addition problem. To add matrices, first, they must be the same size or must be the same dimensions. So they have to have the same dimensions, and then you're just going to add elements that are in the same position. You're going to combine like elements, okay, which means add the elements that are in the same position. Which is why they have to have the same dimensions, because if I want to add, if I have an element in row 3, column 3, then the other matrix has to have a row 3, column 3 for me to add it with. So let's take a look at this letter A, which we're supposed to add matrix A and matrix B if possible. Matrix A is a 2 by 2. Matrix B is also a 2 by 2. Will we be able to add them? Yeah. So to do this, I'm going to write it out just this once, not for all, well, maybe for all of them. I'm going to do 8 plus 12 because I'm just combining the ones in the first position, and then in the second position would be 3, -3 and -7 are added. -5 and 6 are added. 14 and -23 are added. So that gives me a resultant matrix of 20, -4, 1, -9. And I don't know why I put a comma there. It's not supposed to be there. So that's my final matrix, the sum of matrices A and B. For B minus A, I'm going to write out matrix B first. 12, -7, 6, -23. We read them from left to right, top to bottom, just like a book. And we're supposed to subtract matrix A, but I'm going to add the opposite of matrix A. Matrix A's opposite would be -8, -3, +5, and -14. So this is the opposite of matrix A. And now I can combine those to get 4, -10, 11. I don't know why I put a comma. There should not be a comma there. 4, -10, 11, and -37. Let's pretend those aren't there. Try this for letter C. Well, actually, I want to go over letter C with you. You gonna have much adding to do for letter C? B is 2 by 2 and C is 2 by 3. Can you add them? Nope. So there's no solution because they're not the same dimensions. So for addition, we need them to be the same dimensions. All right, scalar multiplication is a lot like it was in geometry when you did dilations and you had ordered pairs that you multiplied by a scalar. You distributed that scalar multiple to both the x and y coordinates. Same is going to be true with our matrices in scalar multiplication. You're going to distribute the scalar multiplier to every element, or to all elements, in the matrix. So you have to distribute it to every element in the matrix. So I have 6 things to distribute it to, and you don't have to draw it. I'm just going to multiply it by every number. This is going to give me -18, -9, 0, 21, 36, and -45, I think. Yes. Try that for letter B. Do scalar multiplication for letter B. That is correct. So when you multiply all of those by -5, here's the resultant matrix right there. Any questions on that matrix? All right, so on the back, I'm gonna do one for you, and you're gonna try one of those 4 problems that are there. So I will let you pick the one you'd like me to do. Which one? B. You want me to do B? All right, let's do B. All right, so according to order of operations, what am I supposed to do first? P plus Q. Can P and Q even be added together? Yes. So I'm going to have 2 times that matrix, and then I'm going to add the opposite of matrix R, and we'll get to that part in a second, because I don't want to subtract. I'm going to add the opposite of matrix R. So P plus Q is going to be -2, 9, 12. I'm just adding the elements in the same positions. -12, 2, 4. Now I'm supposed to do my scalar multiplication, which is going to make that become -4, 18, 24, -24, 4, and 8. Just multiplying every single element by 2. Now we're going to add to that the opposite of matrix R. Matrix R is right here. It also, this might not be possible, but it is because it's also a 2 by 3. Since we're adding to all two, since all of those are 2 by 3s, this whole thing is possible. So we're going to do the opposite of 5, +1, 0, the opposite of -1, the opposite of 2, the opposite of 10. And now we can add these together. We get a final answer of -9, 19, 24, -23, 2, -2. Any questions on that? All right, guess which letter you're going to try? D. Yup. Nope, not A and C. I'm not worried about those. I mean, we could look at those, but they're all the same matrices, so we're okay there. I'm going to ask you to try letter D. Let's see size. All right, please check your answer. If you correctly multiplied S by a scale factor of 2, you got the matrix in pink. And then to subtract, I did the sum of T and S in here, and I changed, oh, it's frozen, sorry. And I changed the sign, so this is 2 times S. The black was T plus S, and then I distributed the negative by changing the sign. So you see that in red, the sign was changed on all of what was T plus S. And then when you combine the elements that are in the same position, your final matrix is right here in red. -1, 4, -4, 8, -7, -11. All right, so now we're on to the next and probably the most challenging of the basic operations for matrices. Addition, pretty straightforward. Scalar multiplication, pretty straightforward. We just finished doing combinations of those. We're now looking at matrix multiplication. You may want a spare sheet of paper when we actually go through and do some of the calculating. So I want to make a note. You know how for addition and subtraction they had to have the same dimensions? Matrix multiplication doesn't necessarily work that way. They could have the same dimensions depending on what they are. But let's put it this way. A times B can only happen if and only if we're going to look at their dimensions. So A times B, the product of matrix A and matrix B. So not scalar multiplication, but actual multiplying 2 matrices together. Can only happen if we have, here's the rows of A times the columns of A. That's the dimensions of matrix A. Rows of B times columns of B. That's the dimensions of matrix B. These two right here have to match. The two middle, the columns of matrix A and the rows of matrix B must be the same. If they're not the same, then you cannot multiply the matrices. The columns of the first matrix listed in the product and the rows of the second matrix, when you look at their dimensions, have to be the same or it's not possible. In addition, the size of the resultant matrix or the resulting matrix will be the rows of matrix A the columns of matrix B. The rows of matrix A and the columns of matrix B. I'll give you a numerical example in a second. But that's the test, to see if you can even multiply them. For addition, they have to be exactly the same dimensions so that all the elements match up. Here you don't want them to necessarily be the same. You want to make sure that the columns of the first matrix and the rows of the second matrix are the same. If that's the case, you can multiply them. If it's not, you can't. Now, let me give you some examples. This is where it's going to get crazy. We're going to want some space over here. I'm going to do some variables for matrix A, some variables for matrix B, some variables for the resultant, and I'm going to show you how it's calculated over here, and then we'll do some number examples. So here's matrix A. I'm going to have, matrix A is only going to have 2 rows and 2 columns. I'm going to call this one matrix A. And so our rows and columns, I'm going to fill in the elements with letters A, B, C, and D. I know, very creative. We're going to be multiplying matrix A by matrix B, which I want to do in a different color. We'll do it in pink. Good suggestion. Also going to have 2 rows and 2 columns. Doesn't have to be the same, but we want this columns, 2 columns, to match the number of rows here, and it does. 2 and 2 match. I'm going to call this W, X, Y, and Z. So this was 2 by 2, this was 2 by 2, and the inside dimensions match, so we're actually able to multiply them. What size is our final matrix going to be? Not 4 by 4, 2 by 2. It'll have 1 row, it'll have 2 rows and 2 columns. This will be the answer to A times B. It will also be a 2 by 2. Those 2's coming from the outside numbers. All right. This element right here is going to be called row 1, column 1. There's going to be 4 elements. This row right here is called row 1, column 1. It comes from, now get this, right? The columns of A and the rows of B had to match. This is going to come from row 1 of matrix A with a type of product of column 1 of matrix B. I'm going to show you what that looks like. I'll show you that work over here. Row 1, column 1 is going to be calculated in the following way. How many elements are in this row and this column 2? The first elements get multiplied together, the second elements get multiplied together, and they get added together. So it will be A times Y, or no, A times W, I'm sorry, plus B times Y. So the first elements get multiplied together, the second elements get multiplied together, and they get added. To calculate row 1, column 2, which is our next element located in row 1, column 2, we're going to pull from row 1 of matrix A, column 2 of matrix B. So again, we'll have this time we're going to have A times X plus B times Z. So the first one's A and X multiplied together, second one's B and Z multiplied together, and add them up. Our next element is in the position row 2, column 1. So now I'm going to take row 2 of matrix A, column 1 of matrix B. So that would be C times W plus D times Y. Questions on where those are coming from. And lastly, we're going to have row 2, column 2 position to fill. Row 2, column 2 position comes from the product. It's from row 2 and column 2. So C times X and D times Z. CX plus DZ will give us the number for that space. So there's only 4 numbers for this, but I have to calculate them in this way. So this is an example of it using variables. I have a handout that I'll give you tomorrow. I thought I printed it off, but I didn't. It's in color. It gives you a little bit more detail about this, but this is a pretty good example, and once you see it with numbers, you'll start to get it a little bit better. So we're going to see if these are even possible before we try them. The first one that they want us to try is to do the product of matrix A and B. A is a 2 by 2, and B is a 2 by 2. So is it possible? Or actually, B is a 2 by 3. So is it possible? Yes. And the size we're going to end up with is going to be a 2 by 3. I'm going to do my work. I'm writing big, excuse me, because I'm going to do my work on a separate sheet. So I'm going to have 1, 2, 3, 4, 5, 6 elements. And I'm going to do this on this separate sheet of paper here. So row 1, column 1 is going to come from row 1 of matrix. Let me write out my matrices on the paper too before I do this. Here's matrix A. 3, -1, 4, 0. Here's matrix B. I always want to put them left, whatever one's first on the left of the other one, even if I'm multiplying a different order. I need to make sure that whatever one comes first in the statement is on the left as I multiply. -2, 0, 6, 3, 5, 1. So for row 1, column 1, which is the first position I'm supposed to fill, I need to use the rows from matrix A and the columns from matrix B. So I'm using these rows. I'm not going to label the columns in A, and I'm using the columns from B. So row 1, column 1 is going to be 3 times -2 plus -1 times 3, which is -6 plus -3, or -9. My next element is going to be right here at row 1, column 2, that position, row 1, column 2. So again, I'm going to use the row 1 elements from matrix A, but now I'm using the row 2 elements from matrix B. So 3 times 0, -1 times 5. So that's 0 plus -5, which is -5. The third position that I need to fill is in row 1, column 3. So row 1, column 3, again I'm going to use row 1. This time I'm going to use column 3 from matrix B. So 3 times 6, -1 times 1. And then add them. So that's going to give me 18 and -1, which is 17. Questions so far? All right, now I'm going to continue this process to find the other elements. So the next one I want is right here. It's row 2, column 1. So I'm going to take row 2 of the matrix on the left, multiply it by column 1 on the matrix on the right. So that's 4 by -2, 0 by 3. So that's going to be -8 when I add those together, because it's 0 and -8. My next element is located in position row 2, column 2. So there's my row 2, here's my column 2. 4 by 0, 0 by 5. Well, both of those are 0, so the element's going to be 0 when I add them together. And lastly, I have row 3, column 3. So I have to use, not row 3, geez, row 2, column 3. So I have to use row 2 and column 3 to get that last element. That's 4 by 6 and 0 by 1. So that's just 24 plus 0, which is 24. So here's the product of those two matrices, matrix A and matrix B, multiply out to this new matrix. We'd use the rows of the one on the left and the columns of the one on the right when we're looking at the order of the product. Let's take a look at letter B. Is letter B even possible? Yep, that's a 2 by 3 and a 3 by 2, which this is going to be nicer because instead of getting 6 elements, we're going to get 4 elements. It's possible because the two there are the same. So I need a row 1 and a row 2, and then I need a column 1 and a column 2 in my final matrix. Well, I'm going to write these out. B I put on the left, -2, 0, 6, 3, 5, 1. C I put on the right, 2, 0, -1, 0, 9, 3. The first element I need to find is row 1, column 1. So I'm going to use row 1 from B and column 1 from C. I'm also going to mark that I'm using the rows of B and the columns of C. So I get -2 times 2, 0 times -1, 6 times 9. That's going to give me -4 plus 0 plus 54, which when I have 54 and -4, it gives me 50. For my next element, which is located in row 1, column 1, again I'm going to use row 1, this time I'm going to use column 1. -2 times 0, 0 times 0, 6 times 3. So it's 0 and 0 and 18. I don't need you to write this out every time. The first few times you will want to, just to make sure you're doing it correctly. But after that, if you are quick and efficient at it, you could just be plugging this into your calculator or writing down real quick the products. -4 or 0, 0, 18, and then you've got your number when you add them up. Row 2, column 1 is my next element. It's located row 2, column 1. So I'm going to use row 2 and column 1. 3 by 2 is 6, 5 by -1, 1 by 9. Add them up. I get 10. And my last element, row 2, column 2, is what I'm trying to fill. Well, here's my row 2. Here's my column 2. 0, 0, 3. Which is 3. Any questions on where those elements came from? All right, let's take a look at letter C. We're asked to do the product of A and C. A times C, A is a 2 by 2, C is a 3 by 2. Could those be multiplied in that order? No, because those dimensions don't match. However, could C times A work? 3 by 2 times 2 by 2 could work because the middle dimensions match. You're going to end up with a 3 by 2. So you'll have 3 rows, which are coming from C, and 2 columns coming from A. As you set up this problem, because you're going to be doing this in a second, you want to make sure you write C to the left of A. You're going to be using its rows. row 1, row 2, and row 3. And for A, you write it to the right of it, 3, negative 1, 4, 0. You're going to be using its columns, column 1, column 2. Please try that. See if you can fill in these 6 elements accurately by doing the multiplication of those 2 matrices, row by column. All right, the final answer you should get is up there right now. In a second, if you didn't get those, I'll go over individual elements with you if there's a specific element you did not get. And that's the end of the video.